So, next is the strain or tension insulators. So, strain or tension insulator are designed for handling mechanical stresses at angle position where there is a change in the direction of line or at the termination of the line. You might have seen, I am roughly sketching, it is something like this. You can observe that suppose this is the line. So, this is insulator sting, it is insulator sting only, and it is coming like this. So, this is the cross arm, it is connected, and suppose conductor is connected here. You can see these are all the insulator pieces, say. So, conductor is coming from somewhere, you see the horizontal it is placed tension string, and when it is line is going out, either I mean when line coming from, suppose a line is coming like this direction, and when it is taking this direction something like this or angle, any angle direction, then you will find at that point it will be your tension type, it is horizontal position it is kept. And either another thing is that for another side, suppose if you have you want to take the same horizontal thing, then another side also maybe insulator pieces are there like this, it is there, and this side conductor is there. So, this is conductor, this is also conductor, but you have to connect this. You will observe that this is connected like this by the same conductor. If you observe on the high tension tower, you can see that. So, that means strain type. So, and sometimes it is coming in horizontal position from some, suppose conductor is coming like this and going like this. So, somewhere it will be tension type, it will make it horizontal position, so that conductor will be tension, and from there again you can find out another one, maybe the same horizontal position, or maybe depend on the design, or maybe you will find it is coming on the your what you call the horizontal position, another maybe vertical position, but it will be connected to your what you call, it will be connected to that your this thing by this same conductor. You can observe it that when insulator is going connected somewhere in the tower, and when it is suspension type, that it is like this, it is like another tower is here, say it is like this. So, conductor is connected, so it is going like this, right. But question is that when it is coming from somewhere and suppose taking another direction, so either it should be either side you can see horizontal type, or sometimes you can see it is coming like this, and after that some other cross arm, maybe that string insulator is coming, and from there I mean it will be something like this. If it is not like that, it will be something like this. From another cross arm, I can make it like this. So many strings are there. So, conductor will go like this. So, in that case this point and this point you have to connect, because this is conductor end, this is also conductor is this thing. So, if you join this conductor, suppose this is not there, this is for this one, I draw a separate thing. Suppose you have this insulator string, that is horizontal position, this conductor is coming from somewhere, this is your conductor, Say another cross arm from the same tower, maybe it is a string insulator, vertical position, this is another one, right. When it is coming and changing the direction, then that is your coming from one direction, that conductor taking not necessarily 90 degree, but taking in another direction, maybe pin, then this portion should be connected like this conductor, right. Otherwise how the continuity will be maintained, because this is insulator, and there it is connected, this is your tower, right. So, this way things takes place. So, if you observe your high tension transmission line anywhere in front of your house or college or whatever it is, if you see this, then you will see that this is the different way it is connected. You can see V shape also, V connection. So, that is why these strain or tension insulators are designed for handling mechanical stresses at an angle position where there is a change in the direction of line or at termination of the line. At the termination of the line also, not only for high tension line, even low tension line also, at the termination point you will see the insulators are connected horizontally, it is kept in tension, right. Sometimes in the railway traction, if you look also, you will see the same thing, any railway station you just try to look at that, although that operate at 25 kV, but design is little different, but you can have a look on that, right. So, for high voltage lines having larger spans and greater mechanical loading, suspension insulator strings are arranged in a horizontal position. Suppose that is why I told you that rather than vertical position, you arrange it horizontal position, right. So, in case of a single string is not sufficient to take the load, two or more string in a parallel may be employed for higher conductor tension, right. That means, suppose it is something like this, suppose from the say cross arm you have one insulator, suppose if tension I mean line loading is very high, another cross arm you have this, right, you have this. So, two string of insulator and conductor is connected here, you can observe that thing also. Whenever you are traveling by train or anywhere your high tension line, look into that, you can see different type of insulators are there. It depends on the your voltage level, and it is double conductor or 3 conductors in each phase. Several things you can observe, even 4 conductors in a phase. You can see that. I recently I went somewhere, I found in each phase there are 4 conductors, right. So, question is that there is a change this thing for high voltage lines having longer span, because for high voltage line the span will be longer and greater mechanical loading, because conductor size is more, that mean cross sectional area of the conductor is more. So, suspension into strings are arranged in a horizontal position, that is to keep them in a tension, that is why it must be in horizontal position, and in case of a single string is not sufficient your this thing to take the load, 2 or more string in a parallel may be employed for higher conductor tension, like this 2 or more you will be there. You can observe it is connected like this, you can observe that they are in parallel, right. And if it is, I told you that for high tension line I told you that sometimes it is connected like this, that suppose this is the tower cross arm for example. So, these are insulator string I told you, suppose conductor line is coming from somewhere connected here, and from another side, that just schematically I am showing that this is your insulator thing. So, conductor has this is the your conductor, but these two has to be connected, right. If you look into that, it has to be this thing connected, right. So, in case of a single string is not sufficient to take the load, 2 or more string, I just show you that how it should be connected. That is only connection of the insulators, right. Now, another thing is that is V connection, V strings. So, this is also just see if I have any diagram for V strings, I can show you. I think I have missed somewhere. So, a single string, V string means it will be connected like this, it is connected like this, another side insulator will be like this. These are all the pieces, right, string, it are all the pieces, and this is the conductor point. So, conductor will be connected here, this is actually V string, it will be like connected like this. So, this is actually V string. So, advantage of this one is that a single string of insulator follows the conductor and sways like a pendulum in a strong side wind. So, V strings are used to prevent conductor movement at towers, right. So, if it is connected like this, either one is this one, another is this one, this will both the side insulators are there. So, it will balance that one. So, conductor swing will be very less, minimum, that is why this V string connection also you can observe, I have seen it many places, right. So, this your what you call V strings are used to prevent conductor movement at towers, but they find increased application in high voltage transmission system, because high voltage transmission system conductor itself is a cross sectional area is very this thing high, and V string construction offers the following advantages, right. If I search the figure, it is marked as figure 9. If I get the figure where I have kept it, I will show you, just 1 minute, if I have I can show you, otherwise anyway I showed you that how it is connected, but as it is mentioned figure 9, I will see if it is there or not. Here it is here, I got it, right. So, this is actually V string, that how it is connected, right. The one conductor here, one is here for 3 phase line, this is the tower, that how that insulators are connected, whatever I showed, that such that there will be no swing of this one. This is actually figure 9, this is V string. So, so to find increase of V string conductors offers the following advantage, it has some advantages. The insulator swing is reduced naturally, and therefore, lesser spacing can be provided between the conductors. That means as if it is connected like, but look at that, 2 insulator strings are used. So, their insulator cost will be higher, that is also another aspect, right, because 2 insulators are used, but as the conductor swing, our conductor movement will be very less. So, distance between the conductor, so this is our phase, one phase, this is another phase, this is another phase. So, distance between the conductor, it can be kept minimum, right, but it will be expensive because you are using this side one in each tower. So, it will be expensive, right. So, right of way width is reduced, that is true, because it will not take much space, and your then reduction in phase spacing reduces the reactance. You have studied transmission line inductance calculations. So, there we have seen it, those who have taken the power system analysis course, there we have seen it. So, and or we have read it in any book. So, reduction in phase spacing reduces the reactance and the system power limits are higher. So, you can raise the power limits. The sizes of the tower and the cost are decrease, naturally it will decrease, this result in saving in cost, and your lightning performance is improved. V strings are particularly suitable for single circuit lines. It is suitable for single circuit lines because if 2 circuit comes, the number of string will be doubled, right. So, generally it will be expensive. So, V strings are particularly suitable for your circuit this thing single circuit line. So, high voltage line it is better. Single circuit means in each phase there will be only one conductor, right, one circuit. And insulator materials. So, overhead your overhead line insulators are produced from toughened glass or high quality wet processed porcelain. Porcelain is very common, there is a toughened glass also used for high voltage, but your porcelain is very common. The materials, little bit idea you have to have for insulating materials. Porcelain insulators are usually glazed in brown color, that also you have seen, right, overall exposed surface that you have seen, but sometimes cream glazed insulator are also used, right. So, toughened glass insulators have their surface layers in state of high compression, due to which their resistance to withstand mechanical and thermal stress is greater, at the same time expensive also, right. And the toughening process consists of heating the glass uniformly to a temperature above its strain temperature, and then it is then allowed to cool usually by blowing air on its surface, right. So, this way mechanical strength of this glass is increased, toughened glass rather. So, some of the your what you call this is some general idea you have to have, at least from general knowledge point of view. So, some of the advantages of toughened glass insulators over porcelain insulators are, right. The toughened glass insulators have greater puncture strength, this is true. They possess greater mechanical strength, and therefore, there is less breakage in transport and installation, this is also true. They have high thermal shock resistance, and therefore, damage from power flashover is very much reduced. The life of a toughened glass insulator is long. These are the your what you call the advantages, right. Just 1 minute. Next, if an insulator is damaged by electrical or mechanical cause, the outer set breaks and falls on the ground. The cap and pin remain sufficiently strong to support the conductor in its position. The glass insulator has the disadvantage that moisture readily condenses on its surface. This is a disadvantage. Most of the lines use porcelain as an insulating material, but toughened glass insulators have also been used up to 275 kV and at 380 kV. I mean in general above 220 kV line the toughened glass insulators are used, right. So, but in general rest of the thing you will find that these are mostly they are porcelain, whatever I have seen here and there, they are mostly porcelain type of this thing, porcelain made insulators. So, now table 1 shows the some characteristic of porcelain and glass for the purpose of comparison. So, some table is here, this is the characteristic of insulating materials, right. This one is your characteristic tensile strength, this is kg force per millimeter square. In the case of glass it is 5.35 to 8.53, whereas in the case of porcelain it is 4.23 to 6. That means this strength is your tensile strength for glass is higher. Then crushing strength, in this case it is again kgf per millimeter square, it is 8.52 to 35 say 0.2, and whereas it is 31 to 42.6. Crushing strength of porcelain is more than your glass. Then modulus of your elasticity, right. So, this is kgf per millimeter square, here it is 5000 to 8500 and here it is 7000 to 10500. So, porcelain case is high. Coefficient of expansion, in this case it is 7.9 10 to the power minus 6 to 8.33 10 to the power minus 6, but in the case of porcelain it is 3.33 to 10 to the power minus 6 to 6.6 into 10 to the power minus 6. Now, density, in this gram per cc it is 2.49 to 3.46 and it is 2.21 to 2.35. So, it will be heavier because the density is higher compared to porcelain. So, toughened glass will be heavier, right. Then punch strength kilovolt per millimeter, here in this case 70 to 120 and here it is 12.5 to 27.5. So, punch strength is much higher for the toughened glass compared to porcelain. And dielectric constant, this is 6.8, it is much higher than I will not say much higher, but higher than porcelain where it is 6.15. So, these are the difference between that glass, toughened glass or porcelain, and they are your what you call different characteristic 1, 2, 3, 4, 5, 6, 7 characteristics, these are the differences. So, with this just I say before going to mathematics part, with this we would like to tell that insulators are of pin type or suspension or what you call this suspension type are mostly used particularly in the high tension line, and anywhere you can see that your suspension type insulators are there. So, in each insulator or each string each string there will be several pieces. So, each one will assume that it is a formation of something like a represented like the shunt capacitor, and whenever it is that is between and same thing that there will be a cross arm and supporting tower. So, capacitance will happen between that your tower and that your what you call that insulator pieces. So, that thing has to be considered. So, now how the voltage distribution of insulator string, right, over insulator string, how things will happen. Suppose this is your cross arm, because insulator are hung from the your cross arm, and this is your support, the tower, this is the support tower. So, you have suppose you have n number of strings, for example, so many strings are there, sorry, n number of your pieces are there in a one string, each one we are asking this thing, each one having equal capacitance. So, each one represented by equal shunt capacitance. So, C, and voltage across this one, say each one is V1, then next one is V2, then V3 like that, and for nth piece it is your Vn, for n plus 1 piece it is Vn plus 1, right. And from your from each piece to that support you have a shunt this thing, you have also a capacitance. So, it will be C, then it is multiplied by Kc, K is a fraction greater than 0 less than 1. So, everywhere we are assuming these are all Kc because all are equal distribution, right, and voltage is V1, V2, Vn like this up to Vn plus 1, and at the bottom the line is connected, at the bottom that conductor, this is the conductor is connected. So, this general figure. So, voltage distribution across an insulator string. So, now what I said, a string of identical clean and dry units with no metal work in its proximities shares the applied voltage equally among the units. So, there are so many units in each string, right, and each disc can be considered as a capacitor C. That means, you have so many discs, I showed you that in that your suspension type insulator. So, each disc can be considered as a capacitor C. So, this is the each disc considered to be as a capacitor C, and the complete string acts as a capacitor voltage divider. The whole string it acts as a capacitor voltage divider, right. In actual practice, the earth tower is present nearby, right. So, each metal cap and pin joint has a capacitance to the earth tower. So, each metal cap and pin joint, right. So, everywhere this one, this Kc has a capacitance to the earth tower. So, this is actually support. So, this these stray capacitance have an important effect. These stray capacitances have an important effect on the voltage distribution, as a result of which the voltage across a unit nearest to the line is more. That means, here because of this stray capacitance, voltage nearest to the line, this is the line, and this is the your what you call that unit. There are several units, it is string, right. So, it will be higher. So, that is that this effect on this is that voltage distribution, result of which the voltage across the unit nearest to the line is more than the voltage across a unit situated near the tower end. So, this is actually this is the tower end, and this is your near to the line. So, voltage will be more here than this one. So, the string efficiency of an insulator of n units, suppose in this string you have n number of units, say in this string you have n number of units, this string n number of units, then string efficiency will flashover voltage of the string divided by n into flashover voltage of 1 unit. Other way you can write voltage across the string divided by n into voltage across the lowermost disk. That means, voltage across the lowermost disk is that this is that lowermost disk, right. And you have total n number of in this case I will tell you it is n into flashover voltage of 1 unit and flashover voltage of the string. So, total flashover is equal to voltage across the string, whatever voltage will come across the string, total voltage divided by n into voltage across the lowermost disk. So, in this diagram, this is the nth one, this is n plus 1, some more is shown, right. Idea is there should not be any confusion from this diagram actually, right. You have the idea is the voltage across the string, you find out total voltage, then n into voltage across the lowermost unit. Suppose in this case, if this is the nth unit, say forget about this thing, you forget. Suppose this is the nth unit, then n into voltage across the lowermost unit disk, because this unit disk voltage is higher than this one, right. So, that is why thus the string efficiency decreases with an increase in the number of units naturally. If n is more, then naturally this will be less. So, then figure 10 illustrates the procedure for calculating the voltage distribution. So, this is your figure 10. In this case, you can see, suppose this is the current this n plus 1 capacity this thing unit, right, or we can say n plus 1 capacitance. In this case, current is in plus 1, and part of the current is going to that, this is say I n dash, and here it is nth disk is I n. So, if you apply at this point Kirchhoff's first law, if you apply at this point Kirchhoff's first law, then your I n plus 1 will be equal to I n plus I n dash, right. That means, the capacitance of each unit to the earth tower can be assumed to be Kc. So, all this thing has been taken K into C, K is lying between 0 and 1, right, where C is the capacitance of each unit and K lies between here it is given K lies between 0.1 and 0.2, mathematically it is greater than 0 less than 1, but its value generally it happens in reality it will be between 0.1 to 0.2, right. So, from figure 10, I mean from this figure you can write I n plus 1 is equal to I n plus I n dash. So, I n plus 1 is equal to I n plus I n dash, right. Next, in general we know I is equal to I is equal to, in general formula is I is equal to Y into V, and Y is the admittance. So, I is equal to Y V. So, Y actually is equal to j omega c. So, in general this formula I is equal to V into j omega c. So, this is equation 3. Now, for n plus 1, this I n plus 1 case, you can write V n plus 1 into j omega c, because this is the capacitor of your each unit C. So, it will be V n plus 1 into I n plus 1 j omega c, and this one, this I n dash, first I am writing the I n dash, that is this one first I am writing I n dash here. If you look I n dash for nth one, then what will happen? I am writing V 1 plus V 2 plus V n j into omega kc, because that your this I n dash, that means this one, first I am writing this one, suppose this is the I n dash, the nth one, no. So, is voltage, all the voltage, if you take this one and this one is a common terminal, like this is a common point, this one and this one is a common point, that means voltage impressed across this will be V 1 plus V 2 up to V n. That is why you are writing V 1 plus V 2 plus up to V n into that j omega k c, right, because this point it is a, basically it is a support and tower. So, whole voltage actually across this, whatever is the voltage across this means it is basically voltage across this, these 2 points is tower is common, right. So, that is why we are writing j omega k c, and then I am writing I n, this I n is equal to V n j omega c, this is equation 4. Now, that means j omega c both sides cancel. Then we are writing V n plus 1 is equal to V n V 1 plus V 2 up to V n minus 1, right. That means nth term is added here, nth term, that V your V n into k term is added here. Actually it is like this, just hold on. Actually this equation if you write, it will be your V n plus 1 is equal to V 1 plus V 2 plus, say this way you write V n minus 1, the previous term for this one, plus V n, right, into k plus V n, right. J omega c is both sides cancel, that means V n plus 1 is equal to V 1 plus V 2 plus up to V n minus 1 term into k, and k into V n is added here with this V n. So, it will be V n then 1 plus k, right. That is why we are writing V n plus 1 is equal to V 1 plus V 2 up to V n minus 1 into k plus V n into 1 plus k. This is equation 5. So, equation 5, the voltage across each unit can be written in terms of V n, right. So, that can be written. So, now that means the value of V n can be found by equating the sum of voltages across the unit. So, using that equation, your this equation, the values of your this thing, that values of V n can be obtained, this value can be obtained using this equation, right. Equating the sum of voltages across all the units to the line to neutral voltage. When you take some numericals, you will see. Then the voltage across different units can also be found, right. So, another, this is that simple mathematical derivation. Now, another thing is improvement of string efficiency. Look, it is not possible to make the string efficiency 100%, this is not possible. So, voltage distribution across an insulator string is not uniform. So, this is true. It's because of this this stray capacitance, right. The units near to the line end are stressed to their maximum allowable value. Here whichever that unit near to the this thing line, it will be stressed your what we call the maximum allowable value, while those near to the tower, I mean here near to the tower, are considerably under stress, right, resulting in a waste of insulating material. That what does it mean? That this unit is not under your this thing that your at lower voltage, and units which is near to the line, it has the higher voltage, although you are using the identical insulating material. So, it will be lower stress and it will be at higher stress, that is why you are trying to mean that wastage of insulating material. So, idea should be to try to make as much as possible equal voltage across the each unit, that is the idea. So, the string efficiency indicates the extent to this wastage. So, this is an understanding that maximum allowable value, while those near the tower end are considerably under stress, resulting in a waste of insulating material. Therefore, the string efficiency indicates the extent of this wastage. This is an indication. Although 100% is not possible, but it is your to some extent that you can try to improve the your string efficiency. So, there are some methods for string efficiency is there, such that if you can reduce the shunt capacitance, then there is a possibility to increase the your string efficiency. Thank you, we will be back.